I have this next example. Here I am going to calculate again the enthalpy for a reaction that is measured in a coffee cup calorimeter. The coffee cup calorimeter, remember that it's reactions that are held at constant pressure, so this Q is becoming QP. That's why I can calculate the enthalpy of my reaction. Now looking specifically at the problem that we have in hand, we have the reaction between two solutions. One is silver nitrate, the other one is hydrochloric acid. They're going to give us another compound in solution, and the other one is a precipitate. Yes, follow the solubility rules. Now, another interesting part of this problem is that we are actually given, since we have two different solutions, we are given two amounts. Those amounts are in the form of a volume for the first solution, a volume for the second solution, times the concentration. This is going to give me the number of moles, and we know that from chapter 4 as well. The assumption that I'm going to make in this case is that the volume of the first solution plus the volume of the second solution is going to be equal to the total volume of what I consider now my solution, the overall volume of the solution. Since we're given two quantities, the one thing that we need to check in this type of problems is that whether we have a limiting reactant or not. Volume times the concentration gives us a number of moles. So we have 5 millimoles of silver nitrate. We have also 5 millimoles of hydrochloric acid. We notice that this is a 1-to-1 ratio, and if we look again to the stoichiometry of the reaction, it is actually 1-to-1. It's 1 mole to 1 mole. So we have exactly the amounts of both of the components that we need. So this is a stoichiometric reaction, so no, there is no limiting reactant in this case. The other pieces of information that we're given in the problem is the change in the temperature for the solution. And also remember that in this case, for all these type of problems, both the properties of density and the specific heat capacity for the solution, those are going to be equal to the ones that we have for water. So density of water, heat capacity of water as well. Solving the problem, the only thing that we have to do is to use the now very familiar formula for us, that the heat of the solution is going to be proportional to the mass of the solution, the heat capacity of the solution, the change in the temperature of that solution. The mass, remember that we are going to get it from the volume times the density, and those values are given, or we can calculate them. In the end, we end up having that the heat of the solution, it's actually a positive number, because now we know that the solution is taking in a certain amount of heat that is given away by the reaction. So that's why we now see this change in the signs going from the reaction to the solution. So now what we're going to do is, in order to find the amount of heat for the reaction, the only thing that we have to do is to flip the sign from when we go from the heat of the solution to the heat of the reaction. So we go from a positive to a negative number. So now when we do that, we have to remember that the heat of the reaction in this case, it's also the heat, the change in the enthalpy for my reaction. Now this is our result. Formally speaking, we don't have to do anything further than that. But since the problem is actually asking us to calculate now per mole of the reaction, now what we can do is take this heat of my reaction and divide it by the number of moles of one of the components. So now we selected the moles of hydrochloric acid. This is the heat of the reaction, and then we just take the ratio, we make the conversions that are necessary. Now we end up having that our enthalpy for the reaction in mole of the reaction is approximately equal to minus 67.8 kilojoules per mole.